My name is Eugene Lee, and this is my video report for Lab 1. To start off, the purpose of this lab was to design an experiment using household objects to determine how much excess charge was on a piece of charged clear tape. The models and fundamental physical principles used were Newton's second law, Coulomb's law, the concept of electrical fields, and also gravitational force. As a preview of results, the charge on each tape is 1.7 times 10 to the negative 9 coulombs, and the ratio of the number of electrons stripped away to the number of atoms on the tape was 3.125 times 10 to the negative 7. The materials we used were a roll of clear tape, a meter stick, a flat surface, and two tall and stable objects for support. To make a piece of charged tape, we would first make a base tape and stick that to the table. Then we would cut off around 20 centimeters of tape and then stick that to the base tape. We would then slowly strip off that top layer of tape, which would create the charge necessary. Here are two pictures of the experimental setup, with the picture on the right being the actual experiment. And here is a diagram of what was happening. So as the initial condition, tape B was positively charged and also drooping due to the force of gravity. When we brought tape A near tape B, because the two tapes were the same charges, they started to repel each other. And since the momentum of tape B wasn't changing after a few moments, we can conclude that the net force on tape B was 0. This must mean that the electric force on tape B must equal the gravitational force on tape B. To calculate the charge on tape B, we make two key assumptions. The first is that each U-tape had the same net charge, and this is just to reduce the amount of variables so that we can actually solve the equation. We also assume that both tapes can be treated as point charges, and this is again necessary to simplify the equations. Now onto the data and calculations. Tape B had a length of 16 centimeters and a width of 2 centimeters, and the distance between two tapes was 0.4 centimeters. Using tape B's dimensions as well as the fact that clear tape is around 1 gram per meter, we can get that tape B had a mass of 0.16 grams. Converting that to kilograms and then multiplying that by 9.8, which is the acceleration due to gravity, we can figure out the gravitational force, which is 0.001568 newtons, and that's also equal to the electrical force on tape B. Setting that equal to k times q squared over r squared, we can figure out that the charge on tape B was 1.7 times 10 to the negative 9 coulombs. And then since an electron has 1.6 times 10 to the negative 19 coulombs of charge, we can figure out that tape B lost 1.04 times 10 to the 10 electrons. Then, again, using the dimensions of the tape as well as the dimensions of a single atom, we can calculate that tape B had around 3.2 times 10 to the 16 atoms. And then using that along with the previous calculated value on the last slide, we can figure out that the ratio of the number of electrons lost to the number of atoms on the tape was 3.125 times 10 to the negative 7. To figure out the number of atoms on tape B, we make two assumptions again. The first is that there's a uniform distribution of atoms on the tape, and the second is that there's only one layer of atoms on the tape, or that only the top layer of atoms lose electrons. And this is because the calculations were made in 2 dimensions, not 3 dimensions. There were 3 sources of error in this experiment. One was that there was probably an unequal distribution of charge both on the tape and between the two tapes. The second is that there were probably measurement errors when we measured the distance between the two tapes. And the third was that every time we touched the tape, we decreased the net charge on the tape, which would mean that our calculated values would be smaller than reality. Here is the WebPython simulation. In the picture on the left, we can see that the orange arrows represent the electric field due to tape A, and tape B, which is the top circle, has the two forces, the electric force and the gravitational force. The results of this simulation are identical to the actual experiment because the same data and formulas are used. And we make the same assumptions as previously, which is that the tapes can be represented as point charges, in that both pieces of tape have the same amount of charge. Now, if electrons had positive charges and protons had negative charges, the signs of the calculated charges would be swapped, but none of the actual observations would change because the interactions would still remain the same. Everything would basically cancel out. It's also important to handle the charged tapes as little as possible to ensure that we don't neutralize the charges of the tape too much. Well, that's it for this lab. Thanks for watching.